Good evening, everyone. So we will start in few minutes.
Advanced VLSI Lab was set up in 2012, an initiative by Department of ECE and AEI in collaboration with Sankalp Semiconductor. Primary objective: to bring our VLSI academic framework closer to the industry and prepare engineering graduates for the challenges in the industry. Conducted industry-grade trainings in the VLSI domain. First major research and development activity resulting in a fabricated chip in a 180 nanometer CMOS in collaboration with Sankalp Semiconductor Private Limited and NIST Berhampur, Odisha. Funded by India Chip Program 2016. State-of-the-art information and technology and computing infrastructure with enterprise-grade electronic design automation, that is EDA tools from Cadence and Mentor Graphics, along with open source EDA tools. NDA in place with major semiconductor fabrication founders in the world, giving access to state-of-the-art IC technologies for fabrication. Industry collaboration with major semiconductor companies and skill development institutes to bring world-class research and development experience and industry-grade skill development programs to the engineering students at Silicon. An indigenous, fully in-house chip was designed by 12 undergraduate students in 600 nanometer CMOS technology, fabricated by XFAB, Germany, and fully tested for functionality and performance. In 2019, an extension to the advanced VLSI was added to provide a modern office space environment for industry training and research development work. The lab is equipped with fully networked workstations and AV equipment for fully functional local and remote office environment. In December of 2019, we furthered our goal of bridging the gap by bringing the industry closer to academia. Conducted NES2019, a 4-day workshop, nanotechnology and embedded systems. Eminent speakers from the top semiconductor companies and industries including Synopsys, STM Microelectronics, Savia, VSD, VLSI experts, Tufts University, IIT Kanpur, IIT Kharagpur, IIT Roorkee, KVEC, Makot, and MSEC. The 4-day event electrified the audience with 11 expert talks on wide-ranging topics, 3 workshops, 3 open house discussions with students, and a very insightful panel discussion. In March of 2020, we were proud to have placed 2 of our BTech graduates in Synopsys, a world-leading semiconductor company, for a full-time position. We are also proud to have our graduates working in other leading semiconductor companies such as ST Microelectronics and Micron through our close partner Savia Multimedia. In September 2020, we collaborated with Boston Microtechnology to develop analog intellectual property blocks for a high voltage power management integrated circuit. The chip is fabricated using a 180 nanometer CMOS technology by XFAB, Germany. In 2019, another extension to the advanced VLSI was added, a fully operational industry-grade characterization lab capable of industrial-grade temperature characterization up to 1 part per million accuracy, a capability only few colleges in the world are capable of. Use of industry-standard test and automation tools such as LabVIEW, LabC Windows, and Python.
Hello everyone. So we will start in another couple of minutes. And then we will be ready. So in the meantime, let me just see if our presenters are here. Hemant, I think you're there. Can you just raise your hand so that I can just make you co-host in parallel? Okay. Okay. Just give us a couple of more minutes. Great, guys. So we are about to start. Just hello, Saraswati.
Hello, Puneet. Good evening.
Good evening, sir. So Rajat is here, and I'm just waiting for his team also. So
Okay, great. Yeah, good evening, everyone. Looks like the participants are already in.
I made Hemant also as a co-host. His team. Hi, Hemant. Good evening.
Hi, sir.
Ganesh. Hello, Ganesh.
Hello, sir. Good evening, sir.
Good evening. And the Manisha. Manisha is also there. So hi Manisha.
Hello, sir. Good evening.
Good evening. So all four guys are co-host. Just in case you want to say something, definitely you're free. You can unmute yourself any point of a time. And I know like most of you never get a chance to meet Sarus sir, so now you can see Sarus sir.
Hi everyone. Yeah, we haven't met. We're all tied to our own places now since March.
Yeah.
So Rajat, Manish, who else is there?
So Rajat, Manisha, Hemant, and Ganesh.
Hemant and Ganesh. Okay.
Yeah.
Great.
Rajat is going to I will not say the host the session, but yes, he's going to host host the workshop. And
Right.
the Ganesh, Hemant, and Manisha, so they supported him just to develop the whole tutorial, I would say. And even not even the during the session, but even after the session also. So if any one of you have any questions or you want any type of a support, so these four are always available. I will be there. So I know all these four uh, very well. So any point of a time, if any one of you have any question related to the open source or the flow which they are going to discuss, so you can any point of a time either you can reach these people directly, or what you can do, you can just ping me. I can connect you with these people. But like nowadays, you can just search over the LinkedIn and you can easily figure out, I think.
Right. Right. Yeah. It's a different age now. No visiting cards.
So I think, sir, we can start. It's
So,
already
part
5-5, 136 participants are there, and maybe it's already record. This live streaming is going on, so I'm sure they
okay.
can join us using the YouTube also.
Okay.
And,
Great. So, okay, so I guess the way we're going to start is I'm going to quickly introduce Rajat, and then maybe do like just a 5-minute introduction on open source PDKs, and then Rajat and team can take forward after that, right?
sure, sir.
That good? Sound good? 1 second, I just need to attach this microphone. Okay, all right. So welcome everyone for our 6th talk/workshop. So this is going to be a tutorial on using the open source SkyWater PDK, using open source tool from the whole flow, digital flow from RTL to GDS. And today we'll have Rajat Bansal present this. He's a design engineer at KeenHeads Technologies Private Limited since last 1.5 years. And his current responsibilities are related to synthesis, STA, constraint development, silicon debugging, and supporting roles for that. He has recently completed a full chip STA, and he stepped out a full SoC, system on chip. And he, just like Puneet said, he'll have a his team to help him with the tutorial as well. So this tutorial will present some of the tools developed by the open source community to for the flow, RTL to GDS flow. It will then dive a little deeper and demonstrate the use of open source EDA tools, and along with the necessary inputs for the tools to successfully tape out on various technology nodes. The tutorial also will demonstrate the use of scripting to automate a lot of these flows, because some of these flows are very input intensive and argumentative intensive. So if you don't script them, it takes longer time, source for errors, and so on. The tutorial will also demonstrate the use of, it'll use scripting language, and it'll also demonstrate the EDA tools using the interactive mode. So scripting is usually what's called a batch mode, where everything is just running as command line, and he'll also demonstrate some of these tools using the interactive mode as well, which is the GUI mode, basically. Okay, so before Rajat starts, I thought I'll just give a quick introduction on open source PDK and why it is important now I mean, it's always been important, but it's actually coming to the forefront right now. And why is it important? So I think everyone is, even the younger generation, they have at least seen the last 10 years of the open source movement in software, right? So you've seen pretty much everything, every domain of software is in as open source, like, starting from GitHub to Linux itself, right? The biggest backend for all software tools, Linux is open source software. So if you look at the last 20 years, the open source community in the software has just exploded, right? And you've seen the effect of that. It's just been, just mind-boggling. The kind of development which has happened on the open source side is mind-boggling. But now if you look on the hardware side, especially when I say hardware, mostly I'm talking about integrated circuit. If you see that, it's been basically nothing there. Compared to software, it's basically just been nothing. And there are many reasons for it, but the key reason is actually the PDK. Okay, so I'll just quickly explain what a PDK means, and then explain why having that open source is a key to having a open source hardware as well. So PDK stands for Process Design Kit, and so typically, if you want to fabricate a integrated circuit, so I'll take an example. Let's say I don't even want to do a processor or anything, a simple analog chip, let's say op-amp, right? So if I want to fabricate it, the first thing I have to do is choose the foundry house. Like, where do I fabricate it? Do I fabricate it in TSMC, onsemi, Global Foundries, XFab, or many others, right? So I choose the foundry. So once I choose the foundry, I choose a technology also. So for example, let's say I want to build my op-amp in a 130 nanometer technology, CMOS technology. I choose that technology as well, which is provided by that foundry. Okay, it can't be any arbitrary, obviously. It has to be provided by that foundry. Now, once I choose that technology, that's when I'll sign an NDA and get a PDK from the foundry. Okay, and what does this PDK have? So like I said, if you're not doing digital, let's say just doing a simple analog, it's pretty simple. All I need first is the simulation models. So if I'm using a SPICE simulator, I need the SPICE models. If I'm using Spectre, I need the Spectre models, right? So that's how I simulate it. And I need the what's called the P cells for schematics. So if I'm using a schematic editor, let's say in Cadence, I need P cells for it. If I'm using Mentor Graphics, I need P cells for it. P cells are basically macro cells for the devices which are available for that technology. So basically your NMOS, PMOS, resistors, capacitors, and so on, right? So those are the things I need for schematic. So once I have that, that's the front end part. For back end, similarly, I need P cells for layout. So I want to instantiate transistors directly. My old days, we actually made each transistor with each layer, right? So those are the older days. Right now, you just drop a piece, which is basically a symbol in the layout. So you need the technology file. So technology file means whatever editor you're using should recognize all the layers and all the other information, like your DRC rule decks. So basically the design rule checks, which all of you who attended today's Atul's talk, you know how it's getting complicated. So that process design kit needs to have a rule deck. And LVS is you drew a schematic, you drew a layout. Now, in order to make sure they're actually similar, you need a tool for that, and that's your LVS deck. Then parasitic extraction to make sure your parasitics in check after you've done the layout. So all these technology files are what is part of a PDK. Okay. Now, before all these open source movements, so let's take an example. I went for XFAB 180 nanometer, and I said, okay, XFAB, I need your 180 nanometer PDK. They will give you a PDK for a certain tool because they're closed, they're proprietary. So for example, if I'm using Cadence tools, they will say, we have PDK for Cadence, Mentor Graphics, and let's say some other tool. Okay, these are the three available. And these are proprietary process design kits for tools which are not free. Because let's say I'm a small company or just an individual. Let's say I want to just fabricate chips. It's just very, very expensive for me to buy these tools, right? So if I go for open source tools, I don't have the PDKs to match with that, which means that I cannot design in that particular technology using the open source tools. And that's the bottleneck. So 20 years ago, the price of fabricating IC was too huge. So that was one of the biggest bottlenecks. But now you can pretty much, you can't do in 4 nanometer and 7 nanometer and 20 nanometer. They're still very expensive. But let's say 180, 130, like most of the analog chips are non-CPU or GPU chips, which is almost like half of the world's ICs. You can do what's called multi-processor wafer projects, multi-processor wafer shuttles in pretty much every technology in every fab. And essentially what it is, it's a single wafer where multiple projects are shared. So what happens is then, for example, if I want to fabricate in 180 nanometer in XFAB, if I just want to own the entire thing, like one shuttle, they'll usually cost you anywhere from 100 to 140,000. So basically talking about a crore. If I go for the multi-wafer, project wafer one, then that drops it down to $20,000, okay, almost 6 times less. And if I use a consortium like Europractice or something where I can go even for smaller areas, then that drops down to almost like anywhere between $3,000 to $5,000, which is 3 lakhs, which is much, much more accessible than any other. So your bottleneck now is, so the fabrication cost was the first bottleneck. So that kind of has become a lot cheaper now. Then the second was tools. Tools was very expensive. Now you have open source tool flows for both analog and digital, very well-formed tools. So the third, the last one, which was remaining, was the PDK. So because most of these foundries will not do PDKs for these open source tools because they cost them, and there's not a huge market for them. So they have no incentive to actually create the PDKs for the open source community. So that's where I think the SkyWater is kind of a game changer, because so SkyWater PDK, SkyWater Foundry was actually an old Cypress foundry, which a company called SkyWater bought it. It's actually a part of the Department of Defense in US. It's actually was a part of the DARPA project, the defense project, but now it's available to public. And then Google, I think in May of this year, they actually took that PDK and made it open source. So what that means is that now you can actually get the PDK and change it to whichever way you want, for whatever tool you want. You have full access to it. Obviously, you own the liabilities for it, but at least you have the access. So for now, for me, let's say I was a small company or just an individual, I want to fabricate a chip. I have the open source tools, I have an open source PDK, but obviously I'm restricted to just SkyWater right now because there's no other open source PDKs now, but at least I have that option. And I have a feeling that once this community grows, which is actually is, then more and more open source PDKs will come into the market. Okay, so that's in a nutshell what open source PDK is and why it is important. And so Rajat is going to take it from here. But before he does, just one quick announcement for people who are joining in. Please shut your videos off just to save bandwidth. Whoever is turning on, coming on, just make sure you'll be automatically muted, but just turn your videos off. And before I pass it on to Rajat, if any quick question on what I just said in the last, I guess, 5 to 10 minutes, if you have any questions, I'll take them now. Otherwise, Rajat and team will take it from here. Okay. Actually, Rajat, what you can do is you can start and we'll just watch the chat window. We can always answer them as they come. Okay.
Okay, sure, sir.
Right,
Am I audible now?
Yeah, we can hear you. And,
okay. Yeah. Just sharing my screen. Let me know if it is visible.
So just, I don't know, Puneet, if you can make Rajat spotlight so that way he remains.
Sir, done.
Okay, good. Go ahead, Rajat.
Just a second.
So there is a quick question while Rajat, you're preparing. Maybe I'll answer that question. what does it take to build the PDKs? So I'll give you an example. If you're building a PDK for, let's say, cadence tools, then pretty much everything is written in a language called Skill. Okay, so all your schematics and everything is written in Skill. For verification, if you're using, let's say, caliber tools, then there's a language called SBRF, which is kind of a tickle kind of a language. So you write all your rule decks, so rules for checking design rules, rules for checking LBS, you write in Tickle. For mentor graphics like Tanner, a lot of the PDKs are written actually in Tickle. So whatever is the programming base for that tool, you write it in that program. Let's say you're using the open source tools like Magic, for example, you write the PDKs mostly in Tickle. Okay. Okay, go ahead, Rajat.
Yeah, the screen is visible.
Yeah, it's visible.
Okay, so hello everyone. We are going to talk about the RTL2GDS using SkyWater PDK, as Sarosh sir has introduced many things. So moving ahead, this is our agenda. I will speak about a little of my company, that is KeenHeads Technologies Private Limited. Then next we will talk about the open source availabilities, why we are talking about them, and what all things we can make use of it. Then lastly, we will discuss about the open link flow that is built around the SkyWater 130 nanometer. It has been launched in May 2020. Let's start. So we at KeenHeads, we started in 2016 with the expertise of physical design, and later on we added our DFT expertise team also in 2018. We have a team of 20 engineers with involvement of 60 plus tape outs, with exposure of 7 nanometer, 8 nanometer, 16 and 20 nanometer technologies. What our responsibilities are, basically we do RTL2GDS deliveries along with DFT insertion and physical verifications. Also, we align with our clients' business needs. So what our ownership and responsibility is, we have to satisfy the customer based on their requirements and whatever business needs. So we also help some of our clients to migrate from FPGAs to ASICs. So there are some of our clients, those who are trying their RTLs on FPGA. Once they are able to get the desirable results, we help them to convert them into a SOC. Our mission is to be a proficient, trusted, and reliable partners of our clients. That's our main motto. Then it comes about the values of KeenHeads. So you all might be knowing all 3 points: attitude, performance, ownership. So little bit of it. What attitude we found is like attitude. A person should have a learning attitude. If you have a learning attitude, then there are multiple things which you will figure out your own. You will not get blocked, and these things will be taken care. Then okay. Second point is performance. So once you have your task in your hand, then there are multiple things you would be taking care of. So performance is the thing which you are going to deliver your task. You have to make sure whatever you are delivering is to the commitment, up to the marks. The third thing is ownership. Since we are a small team, a small company, here we have to handle many other things also other than the designing things. So we deal about the ownership, performance, and attitude. Right? Next, who is our boss? If I ask this question to you, you will say your reporting manager or design manager, whosoever it is. But no, we define our boss as the task in our hand. We don't have to please anyone else. The task we have received, if we are doing with the proper maintenance, then we are satisfying our boss. Next one is how well our work deliveries are received. So we used to have weekly sync-ups, weekly updates with our clients, and just to check we are aligned with the track or not. So to validate our deliverables, this is how we do it. The next, am I a powerhouse? So again, when I talk about performance, so when you are attaining an ownership of some task, then you are 100% going to get stuck somewhere. So there could be a possibility that no one is going to help you at that instant of time because all others are busy in their work. So how do you get unblocked from that? That's what we do is we don't wait for instructions. Whatever we do, we figure out ourselves until the time there is a help available. Next is, do we respect norms? So I'm proudly saying that we do not have any enforced policy in our KeenHeads because we ourselves are responsible to take all those things and we protect the norms. These are the values and the vision of KeenHeads. So we all want to stand out as a most trusted, respected, admired, desired, reliable VLSI consultant company in the world, recognized and appreciated by tech giants. So these are our core visions on which we are working on daily basis, and we will surely achieve this vision someday. Next, this is our engagement chart. So since starting until now, so in 2017, we have 2 SOC engagements over 28 nanometer, and we handled multiple blocks over physical design and package designing. Then in 2018, we have networking SOC and consultancy for SDR SOC. Then again, that is on 28 low power and 28 FDSOI technologies. Again, we handled multiple blocks, PD consultancies for SOC. And in 2019, we have 2 SOC engagements over 16 FinFET technology. Again, we handled the multiple blocks along with DFT. So by 2018, we have our own DFT team. So we do RTL2GDS along with DFT and physical verification. And this is 2020. So we have 3 SOC engagements in this year. That is on 16 nanometer and 28 nanometer. We again handled multiple PD blocks, DFT architecture on SOC level and block level. So these all are our engagements. Then this one is the interesting one. This year in July, when the pandemic was going on, we discussed in our team itself then who can take up a charity-based program, which we named later on a KLA, that is KeenHeads Leap Ahead. Basically in Hindi, that is Kala. So what we were aiming in this program is we will help the freshers or graduates, that those are 2020 pass outs or so that they remain motivated and connected with the contents. And what our aim is to add few professionalism in their resume and their way of working. So these blogs are the things which we achieved by the end of October. So we help those graduates with the task planning and management and how to take ownerships. So Linux commands and scripting. So this is the one major thing whenever a graduate enters the industry. The first thing is you have to work on Linux environment. And many of us, we are not that much handy to Linux. So we help them in this. We design some tasks on scriptings and bash so that they can be handy on it. Then also we worked in a team and resolving interpersonal issues. We also programmed for them like resume building, LinkedIn profile building, and then the technical people help them with the understanding of RTL and DFT architectures, ASIC flow, STA, and those things. Those things we try to do on open source tools. So that by that time there was a queue flow which you might be knowing. So we worked on that with them people. By that we also learned and they also learned. So that's what our aim was successfully completed in that. And the next planning for KLA 2.0 is going on. We will start it very soon. That is a good news for you. Now let's start our main agenda of the webinar. Why I should work on open source tools. So once we all know we have industry standard grade tools, as Saroj also mentioned. What is the need of it? So one of the need is the industry tools are very costly. If you are planning to tape out a chip of your own, if you are a startup company, then you cannot afford it on a one go. Other reasons I'm writing out is, again, industry grade sources are not available openly. So we do not have open access to the industry grade sources like those tools. So the advantage here we are getting is in open source, we will get to learn the practical aspect along with the theory and also hands-on on the few of the things of industry grade tools. So basically what open source tools are, they are a little bit of shadow of industry grade tools. Whatever open source community is trying to do is they are just to try and imitate all the features of industry grade tools into open source tools. That's one of the advantage. Next thing is multiple experiments can be performed by picking the input. What I mean to say is here we have open source libraries, labs, clock frequencies we can change, etc. These things we can change on a particular module or design and have multiple results in our hand to compare and enhance our knowledge and understanding. So this is the another advantage. And next is will help many advantages in your interview. Now, how all working on open source tools is going to help you in your interview. There can be multiple reasons, like you have an open source RTL with you and you are doing a physical design over that with the timing analysis, physical verification, layout, and DRC solving. All those things you are performing, then you have a practical aspect of all these things that you can mention in your resume. Another thing, as Saroswar also mentioned, that scriptings are used in between two tools to automate them and uh, uh, make your complete process efficient. So you can design your own project through scripting over these tools. So there are many advantages over which we can discuss. And next is open source. What all things are there in open source? First, we will talk about the requirements of the designer. Now, what designer is, who is the designer I am talking about? Starting from the RTL to GDS, there are various VLSI stages which a design has to go through to get a layout. What all those are? So once your RTL is ready, then there comes a RTL verification engineer. There's a complete team that works on verification of the RTL, that if the functionality is as per the requirement or not. And once your RTL verification is done, then the stage comes to synthesis. And what is synthesis? In that your RTL code gets translated and then mapped with the particular technology node, and then it is written out as in the form of netlist, in which you have your standard cells, gates, memories, IPs, etc., with interconnect information. So that's what one of the kind of engineer. Then later on stage we have STA engineers, we have physical design engineers. So those all are comes under in the form of designers. Okay, so what all they need to have a open source things to do a complete tape-up. So here are a few things which I would like to mention. One is the design. What I mean to design is, design includes specifications such as what would be the area of your chip, what would be the technology node you will be using, what all inputs you will be having, what all outputs you will be having. And then the RTL. RTL is basically code that is written in the hardware descriptive language, which could be Verilog, VHDL, anything. Then comes the constraints for timing, power, and area. So how much frequency you are going to operate your design, how much power you want to have your chip should be draining, how much area your chip should be designed on. So these are come under design. That comes along with the design and RTL. When the designer have the design, now what else is left? Second thing is PDK. PDK is process design kit. What all it includes, this is a set of files of standard cells, memories, IPs with LIF, DDS, NLD, etc. So there are foundries which work on which you fabricate multiple technology nodes, let's say 180 nanometer, 28 nanometer, 50 nanometer. So what they do is they design the particular standard cell in HSpice or Spectre and do simulations and then design the layouts of them. And then they write out the characterized dot libs. Along with them, they write out the GDS of the particular cells. then they create a complete kit of that particular technology node. So they provide, they are the vendors of it, PDK kits. What designers will do, designers will say, I have this design and I want to tape it out on 28 nanometer of CMOS technology. So let's say any of the foundry will provide that particular PDK to the designer and they will say, use this designs. So this is how things work. Then once designer have a design with them and then the PDKs, what the next thing they need? Next thing is EDA tools. Now, why they need EDA tools? Set of tools which helps to analyze the entire chip before fabricating it. So how we work is, we all know, we do not have the chip every time in hand and then do practical testing over it. What we do is we take the help of EDA tools and analyze and simulate multiple times to have less chances of failure in your fabricated chip. So that's what EDA tools help, and these are also required for a designer to have a complete RTL2GDS flow. Once these three things are available for a designer, then he is a designer. Next, what all PDKs are available? So as Professor also mentioned about AXFAB and OSU. So one is OSU. This is Oklahoma State University, which is providing a set of PDKs from all the way 500 nanometers to 45 nanometer. And then comes Sky 130, which we are talking about here. Sky 130 is 130 nanometer, and this is the collaboration of SkyWater and Google. They are providing is technology to everyone. So third one is XFAB. They also provide PDKs from 1 micron to 180 nanometer, and sometimes they are paid, depends on the design and the requirements, but they are less costly than the other foundries. So these are the popular 3 PDKs that are available freely over the web. So we will be more talking about Sky 130, which is the latest one. Then content of PDK. We are talking about we need PDKs and what all things it has. So let's have an example, have a look of it. So this is my PDK. It could be on multiple technology nodes, that is 130 nanometer, 180 nanometer, 500 nanometer. Let's say it could be anything. That could be 28 nanometer or other. Now, for example, if I have a 130 nanometer with us, let's say of Sky 130. So we will have a timing library. We will have a LEF. We will have GDS. We will have a SPICE. We will have Verilog. Now, what all these files are and where they are going to be used, why they are present. The timing library is nothing that contains the timing, power, and area information of each standard cell, and that are basically characterized by the layout designer team. Okay. Then next is LEF. LEF is nothing but it is the design they have made, the individual standard cells they have designed. On that, there are metal layers which are drawn. So the blockages and dimension of those metal layers are present in the LEF in the form of coordinates, which are used later in the stage of LVS or GDS, final GDS tape out. Then again, the GDS. What is this GDS? So one is the GDS we are talking about is RTL2GDS. That is the complete design GDS. That is not this one GDS. What this GDS contains is this contains the individual standard cell GDS. So how final GDS generated is once you have your netlist and that all the standard cells that are being used in your design are there, the tool will pick up the GDS of those particular and then combine them and generate a final GDS of the design. That's the reason Foundry provide this standard cell GDS. So we do not have to design the, let's say, inverter or buffer from scratch. We get them designed. We just have to connect them and place it over a single place. It's SPICE netlist. So What are these spice netlists? These are the netlists written out from the schematics while they are drawing the schematic, which contains the MOSFET information and which type of MOSFET it is, with what are the W and L, what are the connections that has been done in the schematic. What is the use of it? These are used for LVS, layout versus schematic. Once you complete design your chip completely, then you have to make sure if the layout is corresponding to the schematic or not. So that's the LVS. The next is Verilog timing models. So as I said, designing is stage. Once your RTL is prepared, then you have to do a simulation for RTL verification. At that time, once your gate level netlist is available, so verification team takes the timing models of those standard cells, those are used in your netlist, and do the simulations. So this is all. This is the minimum information that a PDK should have, and these all are available in the open source PDKs also. So let's have a look. We will go through all these files and we'll see what all information and what format we are having all these files. So first, we will talk about the libraries. So libraries by SkyWater PDKs. I have this web page on my screen. My Chrome screen is visible. And someone confirm.
Yes, Rajat, we can see.
Okay, so these are the SkyWater Foundry provided .libs. So we will see like this is Sky 130 FDSCHS. What does this means? This doesn't means much complex. This is just high speed .lib. These all are of 130 nanometer. This is high speed. This is medium speed, low speed, low power, and then high density, low leakage, high voltage. So these are the variants on of the .libs which are provided by the SkyWater Foundry. And below is the table. I will have to zoom it out a little. There's an issue with the website. So this might not be visible to you. I will zoom it in a minute. So basically they are showing the difference table. What are the differences of VDD and most device used and all those things between all these memories, all these libraries, those are being provided. PDK kits, those are provided by the SkyWater Foundry. So let's have a look on two differences. Let's say they have a variant of 1.8 volt of VDD to all the way to 5 volt. Yeah, last one is the 5 volt. So in all these, you have 1.8 volt, and then we have a 5 volt PDK kit as well. Then NMOS device used, what all NMOS devices are being used, what all PMOS devices are used, number of inverters and buffers. So how these numbers are coming. So there are multiple variants of inverters and buffer in our .libs. How are there? Because we know we have multiple drive strength and multiple input gates in our .lib. That's how this count is coming. Then AND gate, NOR gate, these count differences there. Then all these things are available. Latches and flops, these are the numbers varying all the way to different technology. Custom power gating, buses cells, macros are also there, USB custom cells, UDP custom cells. More specifically, we want to talk about it. These are the design specifications on which your .libs, your PDKs are been designed. So cell height, cell, yeah, so both are the cell heights. So basically, how your technologies are defined. There are 7 track, 9 track, 12 track. So by here they are mentioning 9 grid, 8 grid, 8 grid, 11 grid. This is how you can have a look on it. Then specifically, if we talk about all those things, so high density standard cell library, what are the features of this library? And it includes clock gating cells to reduce active power during non-slip modes. So nowadays we generally use clock gating cells to achieve power achieve control over leakage power. So that's why we use clock gating sensors. So these are included in this PDK. Then the latches and flops which has been included have scan enable chains. So then new thing which has latestly came into the open sources, DFT architecture. So there are tools for DFT scan chain insertion. So these flops are these flops and latches have scan enable pins with them. Then there are multi-voltage domain libraries. As we saw, they have 1.8 to all the way to 5 volt. Then leakage and routed gate density. All these things, all these are the features of the particular library. So we'll be talking about more about this library specifically. So this is high density SKY130 nanometer. Now I would like also show you how a dot-lib looks. Okay. So I'm working on VLSI Expert server. Now I'm in this directory. So we will see what all contents are here and how a dot-lib looks.
So Rajat, maybe you can little bit zoom it.
Yeah.
Yeah, I think now it's good.
So I'm inside the library directory. Now, as you might have heard, we have PVD conditions, process voltage and temperature. So that can be seen here. This is fast, this is slow, slow, this is typical, typical. And the variation of temperature is all the way from minus 40 degrees Celsius to it is 100 degrees Celsius. Minus 40, 25 and 100. We have three temperatures, and then voltages all the way from this is 1.8 volt to it should have been 5 volt, but it is for 1.95 maximum. So these are the multiple variants on which these standard cells remains the same, but the characterization and operating conditions are different. That's one of the reason we have these multiple dot libs. We will have a look on any one. So I'm going to open this typical 25 degrees Celsius and 1.8 volt lib. Let's see what all content is.
So Rajat, just one small thing. So if the attendees, if you guys are using annotations, so I think you guys should just don't use that particular part, or maybe by mistake. Maybe you can just delete this one, and there is an option as to disable annotation for the other people. You can do that particular part also. So at the top, maybe somewhere where you can just there's a marker thing.
Yeah, marker thing I got.
Yeah, but there is the three dots there. It's if you just click it there, it will say disable participant annotation.
Yeah, it is there.
Yeah, just please do that. Okay.
Yeah,
Great.
thanks.
Thank you.
So this is our dot clip on high density, and PVD corner is typical 25 degrees Celsius and 1.8 volt. So what all is defined, like say a few things we can read out and understand is the technology is CMOS. The delayed models which are being used is delayed lookup tables. Like we have lookup tables for delays in the form of input transition and output load. So that's being used here. And then timing units are defined for time, for voltage, for power, for current, for resistance, capacitance, and then default. There are a few values of default input output cap, input max transition. All these things you will find in this. So one more thing, this is open source .lib, and I have seen industry other industry standard foundries .lib. This is similar to that. This is 99% similar to that. You can understand that. This is not the same. That could not be. This is similar to that. Pattern and syntax, everything is same. So here they define the templates which we will see below the table how to use these templates. So these are the templates, and then these are the library features like VSS to be wherever you find the VSS, that value has to be 0.000. Wherever you will find the V power, that is nothing but VDD, so that is 1.8. These are the mapping, voltage mapping. Then these are the PVT conditions defined again here. For now, here these are defined. The tool, whosoever tool will read this .lib will come to know from this variable that this is process number 1 and temperature is 25 and voltage is 1.8. The tool will report in from this, and the output percentage for transition thresholds 50-50%. Okay, so then this is the first cell. This is A21110. This annotation is also somewhere I've seen. I will show you. So this first section is leakage power, and that is also conditional based leakage power. So you will find leakage power here in this section, and then below you will have the area here. This is the area, and then you will find the timing tables as well with the output pin. Okay, so this all is the internal power section in the form of tables. Yeah, here comes the timing section. So this is the cell fault timing, and this is the complete table for that. This is index 1, this is index 2, and these are the values to be chosen from this matrix. Now, how to use this table? So you might have remembered that we talked about the templates. Now, what to do? We will see this template in the above section of the file. So let's say I am on line number, and this is 498. I will go back at the top and search for this particular syntax, and this is the LU template. So this is the instructions how to use that template. So variable 1 is my input net transition, and variable 2 is my total output net capacitance. Once I have these both values with me, I can compute the delay of any cell, right? So yeah, we talked about like what all things a .lib has. Now, if you see the size of it, so let me go down last line. Okay, so this is 173110. So as we have seen in the website, there are multiple cells with the multiple drive strengths. That's the reason the file is so big. You don't have to go that much of the file, just to figure out all the things which I have mentioned, and that's it. You know what all things are there in .lib. These are sometimes being asked in interviews also, like, have you seen a .lib? This is why I mentioned you will get advantage in your interviews. You can say, yes, I have seen the .lib. I can do calculation. I can, or if I have the input transition and output load known to me, I will calculate the delay, interpolation, and extrapolation doing that. All those things. Then moving forward from .lib. Okay, so these are the multiple variants of it. Then what next? We were talking about is, we were talking about LF. What LF contains is, go one slide back, and here I have a left section. So here's this left. We'll open it. Okay, so this is my left, and as I said, there are metal layer coordinate informations of the blockages and the shape of metal layers which has been drawn. So here you can find the cell. So this was the cell which we read first in the dot left. That is first here in dot left also. So what all things are here? They are defining class core where this has to be sit. Die on the core. The cell has to be set in the core. And what is the origin of the grid? So it will start from 0 0. What is the size of this particular cell? This is the x coordinate and this is the y coordinate. And is the where is the pin A? So pin A has antenna gate area of this. Use signal port, direction is input. What all layers it is taking? Layer L1, Li1. So what by drawing these rectangles on a graph, you will yourself draw the layers that are being used in the formation of this particular cell. So this is the information. This is information that is related to your first cell. This is the left. Again, you can, if you are asked to mention if you have seen any left, real left. So you can say, yes, I have seen a real left and I can draw all these rectangle layers my own. Then I can draw the complete set of layout with dimensions on a grid. This will be available for all the cells as we have all the cells which are being characterized by the foundry. Yeah, this is the left. Then that there is this GDS. So we have GDS directory as well, and you will find the GDS file also. But this GDS file is not human readable. We cannot read it. What we can do is there is a magic RC file, which is basically a script. I will show you how does it look like. So there is a tool called Magic, which is open source tool, and sourcing designed and Magic RC from for technology Sky130A. So what this script will do is this will load 130 Sky130A nanometer technology into the Magic, and after sourcing this script, you can read the GDS. That will come up in your screen, and you can see visualize the GDS of this particular individual standard cells that has been available in your PDK kit. So this is GDS. We'll see some spice netlist. So we talked about a spice netlist, like we have a spice netlist for every standard cell, which defines your most characteristics. So yes, again, we got the first cell as A21110. So for this cell, you can see these are the pins A1, A2, B1, C1, D1, VGD, VN, VPB. These are all the pins of this. Excuse me. For this this is the standard cell. Then these are the number of transistors being used. So there you can see there are N FETs and P FETs being used, and the W width and length of all those transistors has been mentioned here, with the interconnectivity with each other. So let's say this particular transistor, this is N FET, this is connected to this one pin is connected to VGD, another one is connected to D1, then A85193. So you should be finding this number somewhere else also. So we can find it here. So these NFET and NFET are both are connected to each other in some way. And then also this is here also. So this NFET is again connected to this thing, and then here we have PFET. This also connected to that. So this is the interconnectivity information on transistor level for particular circuit. Particular standard cell. This you will find for all these standard cells which have been in your PDK kit. Go then the last is timing Verilog. So we have Verilog. Yes. What we talked about Verilog is used for your simulations uh, once you have your netlist ready. So this is the conditional timing model which is being used by the simulation tools. So this is defining the module. So this was again first module. So these are the module pins and these are the module ports definition. But X is your output and all others are inputs, and wires, internal wires, and their conditions. So this helps the simulation tool to process the waveform and then produce the results as per the netlist has defined. Again, this will also be for the complete set of cells which are being characterized. Apart from this, if I do ls here, we have documents GDS we saw, left we saw, lib we saw, magic again. There will be some layout files for the standard cells. Then techlef is one more thing, which is totally describing your technology, uh, uh, metal informations and other basic informations which are used in the design. So let's see what all informations are there. So their units are defined: time, capacitance, resistance, and database. Then manufacturing grid. So this is the grid distance on which your layout screen will be visible. Then layers. Then this is the site, unit HD, class core. These are the sites where unit SD will start, unit HD DB will start. This is the N-well layer, and what is the property of that. Then your L1, this is the L1 layer. Uh, what is the type of it? This is routing direction, that is vertical. So we have multiple layers in a, let's say we have a 9-track library, and that will have a horizontal, vertical. So L1 is in your vertical, and the pitch and the offset. So this is the x coordinate, this is the y coordinate of pitch of L1 layer. This is the width that of L1 layer. This is the spacing between two L1 layers. So yeah, that's the area, thickness, and edge capacitance. So these are the basic minimum requirements for your physical design that are stored in the techlist. You will find all this information for every layer, every via contact that you are going to use in your design. So we saw the metal layer. Uh, yeah, this is the layer via. So we whatever design component we are using, layers and vias and contacts, complete definition you will find here, that is defined in TechLeft. So you have seen everything. Now you have complete set of PDK. Good to go. Next.
Yes, Rajat. So just to add uh, just one more thing. So guys, now you can see the the PDK and the way Rajat explained you. I'm sure now by now you're 100% sure there are a lot of data is present outside, and it's not like things are not present. And the way he explained, he showed you like, okay, there are the different corners, there are the different when I'm saying the corners in the sense PVD corners related that data is present, PDK is present, and there are different process also. So it's a complete set of data. And he rightly said it's similar to what we usually use in the industry. So don't think like, okay, in an industry they're going to be it's like something different. Obviously it's a subset of the data which we are using. And but for your thing, I think is if you want to do something, you want to design something, if you want to experiment something, for you guys, all of you guys, this much data is more than sufficient. It's not like you just start something with one corner. If you want to do the multiple corner analysis, I think you can do in that particular way. That's one thing I just want to say. Another thing is I'm really appreciate Gyanesh, Hemant, and Manisha. So they all three of you are just supporting Rajat virtually, I would say. So because I can see most of the questions answered by the attendees, you guys are just answering those questions on the fly, and that's a good support. I think it will help Rajat later on. Means Rajat, don't worry, you are not supposed to do anything. These three, your team is handling all these questions very well. So like whenever someone is asking questions, they are just replying each and everything. Good,
Great.
good. Yeah. So Rajat, carry on.
Okay. Thank you. What the next we have is design. Now we will talk about what all design. Uh, till now we have seen what the PDK content is, what, and we know we have PDK ready with us. And design, we already have a design. Let's assume we have design, open source design, they are available, RTLs are available, or let's say you have your own RTL written for full header or something small design that is ready. Now another thing comes is what are the design stages and what are the tools available with us. So we talked about third thing is EDA tools. We will go over each stage and we'll talk about the tools. So first stage is first stage comes is just a second. Not coming up. Give me a second. Hacked it or what?
Yeah, looks like design is saying, okay, I will not come. No, because you explain a lot of things. So
We'll
can
try.
no. So when it's not moving ahead.
Not seems like it is moving here.
Yeah.
It's not moving here. Surprising. And,
Maybe you can just press few more.
next is not working.
Okay, so let's do one thing. Just go to the next slide. Not here directly. Just come out from here.
It's working on all other slides, but it's not
Yeah,
working.
so just go there and just go back. I think that may.
Okay, no worries. I will
So
explain.
maybe you can just do this 15, slide number 15.
Uh-huh.
Okay, just may in the presentation mode and then go back.
Okay.
Okay, nothing. Okay, sorry. So maybe it's not working. Okay, maybe you can just do it, explain in a different mode.
So Puneet, maybe he can just, yeah, do full screen, just the left side reduced a little bit. I think that should be fine, right?
Ah,
These
yeah,
are,
yeah. Maybe he must have some animation. He just want to show that particular animation.
yeah, I've seen this happen with Zoom once in a while. I
Okay.
don't know.
So
If I reshare, that will work.
maybe you can just try.
Okay, let me try this.
Yeah, are you sharing screen or the application?
Resharing screen, I would say.
Yeah, maybe try the application. Maybe it might.
No. So maybe you can just close the presentation and then you can do it if you think you can do that particular part.
Yeah, I can do that. Okay. So the very first stage in our design is we have RTL with us. Now we want to do that. We want to do a synthesis. That what synthesis basically is. Synthesis is a translation of your RTL code that is written in your Verilog that translate into SOP and POS forms, and then optimization is being done. And then finally, a mapping with your technology node PDK that has been provided to the synthesis tool is done. That generates a netlist. So these all three steps: translation, optimization, mapping, and then writing out a netlist. These three steps are the major steps of synthesis tool. These are being done, these are technology dependent. There's a tool called VLSI with us as an open source tool, which does all this part of synthesis. It takes the PDK, that is your library, and then it takes the RTL and then writes out the netlist, gate level netlist. Then for static timing analysis, next stage is static timing analysis. So we do timing analysis has various stages like pre-layout, post-layout, sign-off STA. So for all those things, we have two open source tools. One is OpenTimer and one is OpenSTA. Next comes DFT. So as we were talking about the scan enabled pin are there in the PDK that has been provided by Sky 130 nanometer. So that has this scan pins. That was the requirement for DFT. So for fulfilling that requirement, tool has been came that is named as fault. So this tool, what will do, once your synthesis has been done and you have done timing aware synthesis and it is clean, that fault tool will insert the skin chain and your DFT architecture into the netlist and write out again a new netlist. This is DFT. Then comes your PNR, or let's say physical design stage. The first one is floor planning. So these are different tools which are being used to do a floor planning. Floor planning includes your defining the core and die area, your chip size, and your then it also includes the part of PDN, that is power distribution network. So power planning is also done along with the floor planning. So these all things has been done using init FP IO placer. So basically, as the name suggests, this is initialization of floor plan. So this tool does the floor planning. This is IO placer. So there are input and output ports in our design. So this IO placer places the IOs. This is a PDN tool. So again, power distribution network. It will do the power planning. This is the tap cells. So the IO placer has been done. So this will insert the tap cells for those IOs which has been placed. There is one more tool, that is a gray wolf, which does all those things all along. Then next stage comes is placement. What placement does is whatever standard cells, macros, blocks, IPs we have in our netlist, in our design, that has to be placed in the core that has been defined during floor planning. So these things are being done by replace, resizer, open FISN, open DP. So this is the nomenclature. If you say this is open design planning, there is a stage of design planning, and all these tools are responsible for doing a placement of your macros, standard cells, and memories in the core. Then once your placement of standard cells and memories has been done, so you know our register's location has been fixed. This is not going to change. At that moment, we have to provide the clock to the sequential elements in our design. So since this clock tree synthesis, what does is it generates the clock tree. Basically, it creates a clock mesh all over the design wherever there are sequential elements, and make sure that there is a minimal skew. You might have heard the term skew. So there are multiple reasons why we want to skew minimum. So that's one of the major responsibility of CTS tool that has to be taken care of. The tool is Titron CTS. Once your floor planning placement CTS is done, the final thing left is fill insertion. So there are insertion cells like there are decap cells, there are another antenna cells. Those has to be placed wherever required, wherever design needs it. That is done by a filler placement tool and open TP tool. Once all these things, your placement, CTS, all these things, so base things are done. So what we call base is the things which has to be manufactured in the silicon. That is called as base. So there are, even if you talk about a tape out, there are two types of tape out. There is a base tape out and there is a metal layer tape out. So generally base tape out happens the first, and after a week or so, or depending upon the design, uh, designers used to tape out the metal layer uh, GDS later on. So base is the transistor level design which has to be implemented over the silicon. So that base is formed. Uh, Till here, till fill insertion, there is no addition. Now, after this stage, there will be no addition and subtraction or upsizing or resizing of the transistor. All has been done till here. Now, the left part is routing. Basically, routing, what it is we have placed the standard cells and memories and IPs on the silicon. Now, what we want to do is, what left is, we have to interconnect them with the respective pins what has been defined in the netlist. So there are two tools, that is fast route and Triton route. One of them is does the global routing. So global routing is nothing but the tool understands where the tool has to take the routes from and whatever uh, available sites are there to route. Then Triton route is the tool which does the detailed routing. That takes the responsibility of physically routing each and every interconnect that is available in your netlist. So this, once your routing is done, so you have completely done with your PNR, placement and routing. Physical design, part of physical design has been done. Now what next? Next is spec extraction. What this stage means to. Now these tools, if I talk about industry tools, like we have Innovus or ICC, those tools are also able to do timing analysis within these stages itself. But here, these tools have individual responsibility. They are not sharing any responsibility with any other stage. So here it becomes necessary to have a spec extraction to do timing analysis. So there is a, as I said, we do timing analysis on various stages. So there is this at this stage, after your layout has been done, after routing has been done, PNR has been done, we do a timing analysis and we call it as a sign off kind of STA. For that, we cannot give the dimensions directly to the tool. So what will be written out from this stages, that will be called as DEF, design exchange format. That will contain the coordinates and coordinates of your wires, physical wires, of your devices. Let's say devices, by devices I mean to say that the standard cells wherever they are placed, and all the connectivity that has been happened in the design, that all information in the form of coordinate is available in the def. So this spef extractor, there's a tool spef extractor which takes the def, routing def from the design, and then it will take the tech left, which we have seen a few minutes back. We have it in the PDK kit. There is a tech left which has the layer, each layer information, each via information, everything. Then we have a left which has the particular standard cell metal layer coordinate information. Like let's say if your inverter has been designed in M1, the connectivity, that the amount of metal length that has been used in designing your inverter, that is defined in the left. So SPF extractor will take the def as an input, and along with that will take the left and tech left from the PDK, will map, will basically what it will do is def knows how much number of length the design has taken for routing. Tech left and left knows what are the resistance per unit, capacitance per unit, that will multiply each other and will write out a SPEF. That is your SPEF extraction. So SPEF will contain resistance and capacitance of each interconnect in your design. that will be further used for timing analysis. So there are Elmore models and multiple, there are timing models to calculate the net delay, which we also known as parasitic delay. In morning call, we were discussing your SPAF extraction. That's what it does. Then once we do it, last thing is, not the last, but final thing is we have to prepare a GDS for the tape out. So GDS is streaming out. There are two open source tools which are widely used for layouts. That is, one is Magic, which you I think all know. Another one is K Layout. So these both the tools are openly source available. This can be here. You can view the GDS. You can edit the GDS. You can even check the DRCs also here. Then once your GDS has been generated, now GDS means you have your complete design layout. So we a few minutes back we talked about the LVS. What is LVS? Is layout versus schematic. So we have a SPICE netlist with us that contains the MOSFET interconnectivity and all those things. MOSFET we call is configuration of MOSFET. So from layout, this LVS tool will generate a similar kind of file that will mention the connectivity which is in your layout, and then a line by line comparison will be take place, and then that is a LVS check. So if you get issues here, you have to resolve it. So basically we cannot go back to schematic. We have to verify and check and modify the layout only to get it same as of a schematic. So this is LVS check. Next come is DRCs. So even there could be a question. First we will do LVS or DRC. But what I have seen is DRC and LVS both go hand in hand. There are possibility if you are solving LVS, then you can end up in having DRCs. There are possibility you are fixing DRCs and ending up with having LVS issues. So both go hand in hand. And there are on later stage there are some antenna checks that all can take place on Magic too. So here we started with the RTL. We fed the RTL and PDK kit all the way to JDS. We have covered all the design, all the major design stages. There are much more design stages in between if we talk about industry standards, but open source we have these majorly defined stages and respective tools. Yeah. Puneet sir, will you add something? Also, you might have to say something.
No, nothing. I think you can move forward.
Okay. Next slide we can have over the. So I will show you few tools, like one of the tool is VLSI that has been used for synthesis. Then another tool is OpenSTA. So I will then another layout tool is that is Magic. What I will do is I will just show you how to invoke and how to get hands-on on these tools. So first we'll go for the VLSI. So I have VLSI installed in my server. What I will do is we'll just invoke VLSI. Yes, this is how it is invoked. And now here, if you do help, these are all the commands which are being used and compatible to the VLSI. So what I would say is we will see here which is a read liberty, read cells from liberty file. So we talked about for synthesis we need .libs, which on which your RTL translated SOP POS forms will be mapped. Then we will read the Verilog file, read modules from Verilog file. We will read the Verilog, that is RTL, we will read the liberty, and then we will do the write netlist. So there has to be a command, write Verilog or write netlist, yeah, write Verilog. So how to try this? Go to the link. Just a second. I have this page open. Just a second. sys biosys. What you just need to do, biosys and enter. The first page which opens is clifford.at-biosys. This is all about biosys. What are the capabilities of the biosys? Which language can be synthesized through this? All these things, even downloading documentation, all those things you can get here. Even best part is this is available for Linux as well as Windows also. Because Windows compilers of biosys is also available. Example usage. So what I was talking about is reading a design, read Verilog. This is your design RTL code. Then elaborating it, hierarchy, check top, my top. So my top will be the top module name in your defined in your Verilog. Then the high level stuff. This is proc, optimization, FSM, optimization, memory, and optimization. So uh, here your translation and optimization is happening at each stage. Now they are mapping to internal cell library. So Liberty, they are mapping with the technology, and then optimization is being done. Now mapping of flip-flops to the mycell.lib. So there is a library which they have mentioned of mycell.lib. They will map it with this. Then mapping logic to mycell. So there's a command abc liberty this.lib that will map your all combinational logic to the .lib. Then clean. So clean is basically to remove or clean your intermediate files that have been generated by the tool. And finally, you will write out a synthesized design, that is write Verilog synthesis.lib. So you can practice this in a few minutes. So as I said, Windows compilers is available. You just need to download it, configure it, and then try it out. This is very simple, very simple. You will get a synthesized netlist within few minutes. This is all about biosys. Then next I will be talking about OpenSTA. So again, need to be back PMC. Exit. Okay, so I have STA. Okay, so this is the OpenSTA 2.2 version. Again, this is the timing tool. Here you will do help. You will find all those commands which are being given as a function, as a feature of this tool. So also there are multiple functions before this. So there's a command report 6. So those who knows the reporting command of prime time or tempus, they use report timing to generate a timing report. Here in OpenSTA we have report checks. There are multiple options from price. Then there are fields. If you want to print out the capacitance, slew, input pin, net, all those things, number of digits, significant digits you want. If you want to dump it to a file, if you want to append it to a file name, all those things you can be done. This is just an image imitation of industry standard tools. Also, there is a command called report delay calculation. So this is the command you can give for a path from and to, and then see how the tool is calculating the gate delay and net delay from .lib and spef. Again, how will you practice it? So I have shown the invocation. Let me exit it and come back to the website. So for this, I have it. Just a second. Okay. Just write OpenSTA GitHub. Click on the first link. The OpenSTA is the basically tool of OpenRoad. So if you want, this is again simple. If you want to configure it in your laptop, in your system, just do this. These are the basic dependencies you have to install first. Then you have to configure it. So better this installation. Once you do all these steps, you will be able to go where I just show STA. Then after that, to practice, this community has provided many examples. So go into the examples directory. Yeah, this is here. Here they have given your 3 different .libs. One is slow.lib, fast.lib, typical.lib. This is .lib, one requirement satisfied. Next, we need a design. So here is the design. If you see example 1.v, so this for that contains 3 flip-flops, 1 buffer, and 1 AND gate. This is you can just draw a circuit of this, and this is the syntax of netlist that is available here. Going back, then there are examples, statistical examples. This is SDF and SPEF. For this this simple design, they have provided SPEF and SDF also for doing timing analysis on different stages. So let's see first example. This is the read liberty example, read verilog, link design that will link your .lib with the netlist, and then read SPEF, create clock and set input delay. These both are considered as SDC, your constraint, timing constraint, and then report check. So as we have report timing command, here we have report checks. So this is one of the example. Similarly, they have given 5 examples, 2, 3, 4, 5, different. Download it, practice it. You are a ST engineer then. Next day. Next is magic. Coming back. So here, if I say magic, the tool will invoke magic tool. Okay, this is the visual where you will see all the grids and layout of this, and this is your shell. So this is basically pickle shell, pickle automated tool. So whatever command you will write here, that will result in the output. Now, how will you practice? Again, going to the website and just write magic layout tool. This is originated by Open Circuit Design community, and the link, yeah, as you all can see, this is how your magic layout will look like. They have demonstrated the example of I think that this is of MSP 430, I think so. Yeah, here you can get all the download documents, install documents, how to use technology files, how to invoke it, how to use it, all those things you will get. Practice it. This is also simple. So these are the 3 tools which I have demonstrated you. We will surely discuss about all other tools also in some other webinar. Next, flows around available tools. We discussed about all the tools, all the stages and respective tools which are available with us. Now, what is the need of flow and what are all the flows which are available? So while you're designing small designs, there is no necessity of having a flows and automation around all the tools. You can run individual tool and get your work done. But when you say you are working on millions of transistors, let's say 100 millions of transistors here on your chip in your design, and you have to work on it. So the complete flow individual, if you are doing that, is a bit challenging and risky also. So to avoid both the things, we use automation. Now, from where, how we do automation? That then comes the scripting language into picture, that is Tcl, Perl, or Python. So there are few open source communities that has came up and designed the automated RTL2GDS flow. One of the topmost and latest is OpenLane, and this is an automated RTL2GDS flow based on several components, included OpenRoad. So just now we saw the OpenSTA tool that is provided by OpenRoad, and then these all tools are being included and automated, and there is a complete one script that will run and will take the RTL PDK and will give out you the GDS. That's it. You don't have to do anything. You just have to configure a script where you will mention all those variables and PDK variables and RTL variables. That's it. So we will see about it. Then next available is, as I was earlier talking, this is that the Qflow. Qflow is again a Verilog digital flow that is provided by Open Circuit Design and from end-to-end digital synthesis flow for ASIC designs. Again, this is also fully capable of RTL2GDS flow. We will talk about OpenLane in deep. So OpenLane flow. What is the architecture that OpenLane follows? As I said, The designer need what three things design need? One is the PDK, one is the design with constraints, and one is the EDA tools. So these are the EDA tools at different stages, and open lane flow comes with the automation. So these are nothing but a script that is taking this output and feeding it to the next stage and invoking this particular tool for doing the respective work that has to be done. So starting design is given here, design with constraints, and that is your netlist is faded here, and your SkyWater PDK has been given to this open lane flow that takes the that goes to RTL synthesis. So RTL synthesis again, translation, optimization, mapping, and then writing out a netlist. So this is responsibility of VLSI and ABC. AB is nothing but a subset of VLSI tool only. So overall synthesis responsibility is taken by VLSI. Then it goes to OpenSTA. So this is your timing analysis as synthesis stage, pre-layout stage. Why we are doing it? So you might have heard of a term timing aware synthesis. So this cycle is taking responsibility of your timing aware synthesis. The netlist which you will get here will be timing clean. So independent VIOCs is not capable of doing the timing aware synthesis. That's one of the reason that automation has been done and combined VIOCs and OpenSTA to do uh, timing aware synthesis. Then once you have the timing clean netlist, you will that netlist will go to the fault. Fault is the DFT tool that will insert your skin chain and DFT architecture. Then the netlist comes here. This netlist goes to the floor planning stage. Here there are a few variables also which will be defined as your like aspect ratio, uh, pitch, height, width. Those are available in your tech ref. So all those inputs are being used here. We have provided the PDK at once. We are not going to provide it. The tool will automatically pick up those values from the respective configuration files. Then these are the open road apps, floor planning, placement, CTS, optimization, global routing. All those things will be done. Then the output of from this, what will be the outputs? One of the major output will be def, which has the placement information and global routing information in this, including the CTS. So here you will have a def and CTS included netlist. So both the things will go to the next stage, and this is your antenna diode insertion. There are again custom scripts. So there is no uh, open source tool for inserting in antenna diodes in a netlist. There are custom scripts where automated this flow also. Next comes LEC. So what LEC is logical equivalence check. What is this check for? Now, as you we discussed the design phase of where we have a comparison of like LVS. There is a layout versus schematic. Why we are doing it? We want to make sure the way schematic has been designed, the same way its layout has been designed. That is the LVS. Similar to that, LEC's basic feature is for your checking for logic. So you have taken the RTL and then converted that into a netlist, and your netlist has been getting edited at each stage of your implementation, PNR stage, all the way to here, antenna diode. So your netlist is getting edited at each stage. LEC will check the logic and the functionality between this netlist at this stage and the netlist at this stage. We'll compare both the netlist and result you out if the functionality is remains same, or while adding the cells like at CTS stage buffers and inverters are added, so they might have been added mistakenly into a logic. So that will result out here that something has messed up and your logic is not same as the logic it was here. So that is LEC. Again, VIOSys is responsible to do all those things. Then after that, it goes for detailed routing. The tool is Titan. If there are a few variables like timing aware, power aware, area aware, if those three are not met, and if any one of them are severe, that will again go to design exploration. And if they are not meeting the requirements, and in worst case, we will again go back to the synthesis. So resynthesis will be done for that. Again, this cycle will be uh, recycled. This is how in work happens in industry also. But this is a very rare case by moving from a synthesis to detailed route and then moving back to synthesis. That is very rare case, but it happens. Once your detailed routing has been done successfully, then it goes for RC extraction. You all know why RC extraction is required. It is doing it. What it does is it generates a SPEF from def. So def to stef, def to spef. Then this is the STA. This is a sign of STA with your SPEF and gate delays. Then generating of GDS2, that is final layout. And then once your layout is ready, the physical verification, that is Magic and NetGen. So Magic will take care of the DRCs and NetGen will take care of the LVS. Once all these are clean, this open lane flow will write out the GDS file and left file, which you can hand it over to SkyWater Foundry and ask them to fabricate over the silicon. This is the complete flow architecture. Let's see. Open lane design stages. So we talked about all these stages which open lane offers. But currently there are few stages which are working and few stages are in implementation stage. So what all things are working is synthesis and timing aware synthesis is working. Then there is a stage of floor plan period. If you observe in between, we saw a DFT block. So for now, open lane architecture DFT stage is in implementation stage. It will be releasing in some time. So after synthesis, it goes to floor plan and PDN, and then it goes to placement, and then it goes to clock tree synthesis, it goes to routing, then GDS2. Routing includes your spec extraction also. Then GDS2, that is magic, and then your checks, that is magic will perform DRC and antenna checks, and NetGen will perform your LVS check. That is your logic layout versus schematic. So these all things are currently working in open lane flow. Next is the result directory structure. So in some time we will run a design. We will show you how to a demo on how to run the design. So these are the outputs that will be generated by the open lane. So there will be a design name directory, and then there is a configure.tcl. So what this configure.tcl is, there will be variables and there will be path which are being used for implementing the design. So these are the inputs, user-defined inputs. Some of them are predefined inputs. All this will come together in your TCL file, and there is a directory that is runs. In runs, you will find the tag. So if you have multiple runs, we used to give them tags. Let's say if we are running same design on multiple clock frequencies, so we will name them. This is on 50 megahertz, this is on 60 megahertz, this is on 70 megahertz. That is a tag. Then again, it will have the particular configuration article that will have your logs, reports, results, and temporary files. All these four directories will have CTS directory, floor plans directory, magic directory. Each stage directory it will have. Let's design and have a look over it. What we are going to see is we will run a design using test script which is available. Then we'll go to the run output directory to see what all logs, configs, reports, and results are being generated. Then we will see how to reconfigure and rerun the flow, and then how to update at any stage of design to check the view, how it looks like in Magic. We'll also see how to do ST at various stages. Okay, good to go.
Yeah, I think we can move ahead, or maybe if you want to take 30-second or 1 minute rest, you can do that. Whatever. It's
Your
like
voice is
not.
breaking for me.
Is it?
Now it is fine.
Okay. So I was just saying like, okay, if you want to take 30-second, 1 minute break, you can do it. You're
Okay.
passing a lot of informations to the candidate, and let's see how much these people can uh, use and how they are going to use this particular part. So believe me, guys, the way two things I can see. He explained one is the PDK, what all the different files are present in the PDK. He just gave an idea about what is the information present in those files. And as an engineer, if you remember in the starting itself, he mentioned like, okay, how this open source and open PDK can help you. So there was a one line, it can help you in an interview, and 100% means it's going to help you definitely in an interview. And I can more we will talk tomorrow, but just I just want to give rest to Rajat. So just to share one thing, like yesterday there was a one interview for a one person, and what happened like it is like one of the top notch company. So the interviewer asked like, okay, about the project, and that guy had mentioned like, okay, I have worked in a open STA. And then they asked like, okay, what exactly you have done? And that candidate just answer like, okay, I open the the reports, I analyze that particular part, and I did the calculation manually. And sorry, we checked the calculation manually. So this particular the sentence, like we verified the calculation manually. So that means we whatever with the reports were generated, we verified it using the manual calculations, and just to see like, okay, everything is as per our understanding or not. The interviewer just asked like, okay, how you did that particular calculation. And that guy just mentioned everything like, okay, this is the file, in this particular file this information is there from this table, we pick this particular value from verilog, we pick the cell, we saw the sdc file, we saw the spef file, we saw the dot left file. And so all this information, the moment he explained all that particular part, and the interviewer was impressed. He was saying like, wow, you really did a good job. And his interview is almost like 1.5 hours. Just he conducted that particular part. So the reason I'm sharing this small incidents, like whatever you're going to do in a open source tool, don't think in that particular way like, okay, it's open source, so these are the files. But industry people just always ask the industrial experience, industry tool. No, so they, if you remember, the Shibu mentioned very clearly, they none of the industry people, they are looking you as a champ in a ICC or the Innovus tool. But what exactly they are looking, they are looking like, okay, what are the resources are available, and using those resources, have you just did something using those resources or not? And this is the best example. So the way he explained you, I think you guys should just go back, just try all those things. And I think now he's going to explain about the flow also. I know like, okay, it's going to be by the time he will finish, it's going to be the over the time, but I think that's worth if you will spend time and just stick around for another I think half an hour. The way he's going to explain, it's difficult to give you everything within I think 1 or 2 hours of session, but at least the way he covered that, he covered very well till now. Okay, so and again, once again, thanks a lot, Ganesh, Hemant, and Manisha. Like you guys are saving Rajat time. So it is. It's like it's very difficult for him also just to answer Q&A session. Now there is no need of any Q&A session. That's good. So Rajat, you have all the time. You can speak, and I know like you may be expecting like yeah, you will get half an hour as a Q&A session, but that's your team. They don't want you to just take a rest. Yeah, you can continue now.
So for reference, I have just before this call, before this webinar, I just ran a design and kept it to show you, so that we do not spend 5 or 10 minutes here to run a new design. So what I will show you is I will show this make file and then the make test. So first of all, quickly I will go to the OpenLane page and will show you how to configure OpenLane flow in your PC, in your system, and then how to get started with it, that you can have a practice with it. That's one. Just again, open lane GitHub. First link, open. This is provided by eFabless community. Then here you can go through all this README. What I am focusing on, quick start. So again, git clone, download this OpenLane Git, and then cd to it. Follow these steps and make test. So make test is something which I'm going to show you. I have also followed the same steps. There are multiple ways to run a design. There is a docker command also. This is one of the way also to get the latest pull of your OpenLane as it get updates. So there is a, as I was saying, docker command. So this is the docker command to run any design. For now, I am following this simple steps. That is a quick start. I have done all these 4-5 steps. Now the time is to make test. We'll show you what this make test has been doing. So first I will show you this make file. What all things are there in this make file? Okay. So this is showing the OpenLane. These are the variables, pre-configured variables in the script. Line I am on line number 15. That is your OpenLane directory. Then threads. Achha, one more thing. This OpenLane supports multi-threading. That means you can run multiple design at a single time. You will get to know if you once you read the GitHub page, you will get to know about the multi-threading. So this will check what all threads has been provided. The standard cell library, which one is it going to use? This is going to use high density .lib PDK package, and special voltage library. This one is the different, and this is the low IO library, that is IO. These all pre-configured things that has been in the script. Then the design which we are using is that is USB. That is one of the design presented in their directory, and all these things are your predefined things which will get the complete RTL2GDS flow in one go. Now let's see what make file has been done. So this is basically we will read it out in log file also. So this is showing the version and then sourcing the configure article. So this is the USB configure article which has the configurations. We will see in
Rajat,
some
can
time.
you just sorry to cut you. Can you just zoom it a little bit? So on the user side, they are not able to see properly. One more, I think.
One more.
Yeah,
Okay.
great. Yeah, I think this is a good one now.
Okay. Shall I repeat something or carry on?
No, I think you can carry on. Just
Okay. Okay. So this is the design configuration which is presented in the design config article. We will see this in some time. And this is the sourcing configuration from, again, this is the reading it, and this is configuring that variables. And then this is the PDK routes where our PDK is defined. That is in user bin. That is the path, and the PDK which we are going to use, that is Sky130A. So there are versions A and B. Again, this the behind the story you will get to know once you read the GitHub page. The setting of PDK path is /user bin this, And standard cell library which we are going to use is that is high density. And this is the configuration tool again, preparing left, timing liberty, trimming liberty, preparation complete, running synthesis. So this is your running your synthesis stage. When running static timing analysis, synthesis was successful. So this was printed when your timing was clean. Then it is a running floor plan, then initializing floor plan. This is your core width, core height, that is changing layout. And then there is your floor plan is taking place. You're running decap, uh, extra cells insertion. There's a tap cells and decap cells insertion is taking place. Then there is a stage for PDN generation, power distributed network. So as you can see, this is all automated, and each tool is running one after another. As soon as they get the input from previous tool, that is fed into the next tool, whatever is required, and whatever is required from PDK, that is picked up on that particular stage and being used it. So this is your PDN def that has been generated, and then your placement is done. Global placement was successful. Is again writing out a placement def. We will see all these outputs, where all these outputs have been placed. Then this is writing Verilog. Now your tool is writing the new netlist that has been edited at the particular stage. Then it is running the static time analysis. So this is a stage where your PNR has been done and your extraction has been done. Now this is your post layout static timing analysis. Now this is doing detailed placement, and there will be a stage for CTS. CTS was successful. Then again your global routing, and then your fill insertion is taking place here. Then again it is writing out the netlist, write Verilog. Then your spef extraction, and then timing, and this is again at this stage. So now now work comes for magic. This is generating magic GDS, to checking DLCs, running LVS, that is NetGen, antenna checks, and antenna role checker is running. Then final report has been generated. Design name, run directory, this. So this the tag which we were talking about is this. This is the tag. This has given open link test, and this is our design name. Magic DRC summary. So the total magic DRC violation is 6. So it is showing you the violations also that has been found. So what is the error also that is here? Minimum area of metal 1 holes should be greater than or equal to 0.14 micron square. That's more than required. You're getting your DRC error here itself. What you have to fix, you just need to up the design in Magic and fix it. These are the DRC violations which tool was not able to fix. Some of the violations are there which tools have itself taken place. Then LVS, so there are no LVS. LVS report says no net device pin property mismatches found. So your layout and schematic is properly matching. What is your antenna summary says? Antenna summary says there is no violated pin or pinlet. So your complete run has been analyzed. Now what we will go is we will go to the run directory.
So sorry to cut you, Rajat. So guys, just one thing which is good, the way he explained you. So you might be thinking why Rajat come up with the log file and he explained you each and every stage, and that's something I would say. It's not something everyone is going to tell you, like, okay, that's what is the importance of a log file. But if you want to be a good engineer, like Atul mentioned in the morning session, like we are engineers and we can do anything. So there is a one more thing you have to understand, like you should know how to debug the things. And see, the automation, even if you will see it's run and it will just give you some output. Script is saying no fatal error. That means you will get some result, obviously. But then you will say, like, okay, what next we are supposed to do? And but this log file, if you know how to read the log file, at least this log file is going to tell you a couple of things. One thing Rajat already highlighted, like you can see in the log file is mentioned there are six violations. There are the six DRC violations which tool was not able to fix it. That means what's your next job? Your job is just to open the layout, just fix it, rerun it. Obviously, you have to rerun that particular part or from that particular stage. Another thing is this flow, the automation is written in such a way, like if there is any fatal error, then only it will exit. Else it will not exit. It will just give an error and it will not exit. It will just finish each and everything. So you should know, like, okay, in the log file, where exactly is the error, where the warning, which particular stage they run it, where exactly the tool stops, and all other things. So in the log file, or you can say the report file, that is that should be the very first thing you should do just after running a automated tool. So when I'm saying automated tool, the scripts base any flow if you are running, whether in the industry, in the flow can be based on the Synopsys, Cadence, Mentor, or any other EDA company, or it can be a open source flow. But the what next after running the script? What is the next step? So the next step is you should open these reports, the log files, just see uh, how they are running, and whether they are running a particular stage or not at how in the sense, and what is the sequence of that particular part. So if from the interview point of view, if tomorrow if I will ask you, then okay, you will say like, okay, we have gone through the complete open lane flow. Okay, then I am going to ask you like, okay, what are the different stages there? Maybe you may just see the PDF or the presentation, you can say these are the stages, but that stage maybe in some different sequence the way the flow is written. So you have to understand like, okay, what is the flow sequence, and like what type of messages are there. So those things you have to understand, like, okay, this is the thing. And the interactive session which we were talking about, the Rajat was talking about, like, okay, some interactive sessions, initially the individual tool, basically that's what I'm saying. So then only you will come to know, like, okay, which tool is invoked at which particular stage. And now if you want to rerun it, you can just check the log file. You can see like, okay, if I have to rerun, I will rerun from this particular stage with the help of this particular file, input data, and this particular tool. So you can do in that particular way. I hope it makes sense. Yeah, Rajat. So, sorry, I'm just cutting you again and again because it looks to me like this information is very important for these attendees.
So that is completely fine.
Yeah, please.
Even I would like to say one thing is whenever those who are in the industry already, those people might be knowing it. So whenever you run anything, even synthesis, STA, physical design, anything, the first thing you look at after your run gets complete is the log file. And what we used to do is, just let me show you how we do it. Uh, I'm going in the directory where it has generated all the reports and these things. So here, as I mentioned in the presentation, there is a command log, configuration table, and logs, reports, and these things. So we will go to the log file, and the first thing is we will do grep errors from everything, every files. So here, this is not showing any error here, but what we focus is we focus on errors only. For very first thing we see in the log file is errors. Wherever our tool has stopped or not get the proper input, has not able to move forward. That is the first thing you have to look at, and then debug it, fix it, and rerun your complete flow. That is the first thing you have to take care of. Now we'll go through again. If you see what the things we have here is just a second. Yeah, we have command log. So this is nothing but same what we say and what we So on the terminal, that is written in a file, that is a command log file. So even here, if you see, they have detailed out everything. Let me set the numbers. So first of all, they are running this script, this Python script, and then they are taking tech-left. They are generating a diode2.left. This all these things are taking, and then somewhere they are doing set also, set awk command. These are being used. So this is this detailed log file, whatever they have run. So as I say, if I am a beginner to this OpenLane flow, I want to learn it. So the best way is you run a test case, simple design, and go through the files. Now here is your learning comes. This is the much more faster than going through each scripts and all those things first. You just want to know what this Python script is doing. Just open it and check what this script is doing. This is the best way to learn. Okay, and I talked about configuration file. There are some predefined variables and user-defined variables. So this is my configuration file. Yeah, so this is showing whatever has been used in the implementation of this design. So PDK is to Sky138 nanometer. The library is high density root directory cell pad. So there are IO pads which has to be placed on IOs on die of the chip. That number is 6. Merged left, the path of merged left, and then clock period. This is 12.55. That has been taken from somewhere, and this is used and maintained. The clock port is clock 48. Through this, your clock is getting input in your module. This is the lib synthesis, your trimmed library. So next comes your let's say driving cells. What will be your driving cell? Cap load, max fan out, no flat, 0, max fan out, transition. All these things are configured here from your floor plan aspect of view. There's a core utilization that is 40, aspect ratio is being 1. The IO horizontal metal is number of 4, and the horizontal vertical metals are 3. So you can say that your library is 7-track library. And your V offset, there is P of pitches and offsets for horizontal and vertical power distributed networks. The value of those are defined here. So this is the configuration. This is the complete configuration all through RTL2GDS has been used. Even there are some switches. What do we mean to switches? Run SPEF extraction. This has been given 1. So that means your OpenLane flow script will do a SPEF extraction. So wherever you see a 0, like say this LEC enable 0. So LEC is set off. But the OpenLane flow script is automated in such a way that there are switches. It will check. Do I need to have to do LEC also? Not. So this was defined as 0. So that's the reason the OpenLane script has not done LEC. There are switches and variables which are defined. Now, next thing comes is this is the configuration file. Let's quickly review the reports and results that has been generated. I will go to a report. So in the report directory, you will find that for CTS, floor plan, LVS, routing placement. Let's see for the routing, what all reports are there. So there are antenna report, fast route min-max report, fast route report. There are timing reports. So let's say if I open this timing report, what does it show? It shows no path found. That means there is no violation, right? Then let's open some other report. If I talk about WNS file, this will also not do that. WNS is 0. These reports are checked for checking the violation, if there are any violations or not. Once you have the violation, this will have the timing reports as well. Otherwise, now let's move to the result directories. What we have in results. Again, there are these things. So if you want to do a STA at routing stage from these things, now your run has been completed. Now you cannot intervene in between the flow and check the results. Now what you will do, go to results, go to routing stage. Here you will find your SPEF, and in this synthesis directory you will find your netlist. So what inputs we need to do STA is, we need a .lib, we need a netlist, we need constraints, and that's it. We need SPEF also because we are doing post route STA. So your SPEF is here. You have all these four of things. Launch STA and give all these things inputs, and done. You can do timing analysis. Even though you have no violations, you can generate the timing reports. So that's the beauty of this OpenLink. Then we have gone through the reports and results and logs. Now, next thing what I was talking about is how to reconfigure it. How to reconfigure the script and rerun it. So let's say what we saw is in configuration article here time period is 12.55. Now I want to change it. How will I change it? There are three configuration scripts where you can find all these things. Go to OpenLink directory. Here we have a directory configuration. Do ls configuration, and here you will find different pickle files. One is the general. So let's see what in general it is. In general pickle, you will find the library which is using run magic. So okay, this is the switches. Here are the switches which are going to be used. So here it has been clock period defined as 10. This is one thing. Okay, we'll check another configuration script that is in design. So we are talking about USB design. Go to USB. Then here again there is a config article. This is design specific config article. Here if we see the clock period is defined as 15, but what we saw was 12.55. Now how that was coming? So if you see design specific configuration typical, in that they are defining the design name, that is the top module name, Verilog file, that is the RTL file where it is, clock period, clock time period, clock nets, and the all design required files, PDK files, and log. Like this one is the library configuration tickle. Now we will go to this particular configuration file, and this is also available here. So we know we have done our all those things in high density PDK. So this tickle script has defined 12.55 time period. So the priority of 3 clock period. The first one is this one. This one will be given the priority if I do this modification as 10 or let's say 2.55 and save it and rerun it. Then it will take the time period as 2.55 or 10, whatever you have set. You can change your core utilization. You can change the max fan out cell pad, target density for your placement. This can be controllable. So you just what you need to do is simple. You just change it, modify it, and let's say I have made it replaced with 10.55 and save this file. Now next time whenever I will run this USB with the make test script, you will see the time period will be 10.55. We can run it, but that will take another 10 minutes. But believe my words, that will take 10.55. That's how you can reconfigure and rerun your flow. And you can
believe. So yeah, so if you are saying, then we will believe it.
Okay, so next part is how to do ST at various stages. I already said go to result directory, you will find the SPEF here and you will find a netlist there. Constraints, you already know what clock you are using, what time period is using. Launch STA. That's it. For that, just a second, I have prepared it also. Let me switch to that. Yeah. So I have gathered together all the inputs and place them in run article. Let me zoom a bit for you. It should be fine. So as you might have seen on the OpenSTA GitHub page, the example one was showing read Verilog Liberty. So this is my library which I am using. Read Verilog. This is the netlist that has been added last at CTS stage. After CTS, there has been no changes. So this is my latest netlist which I will be using. This is my link design. USB is my design name. Top module name, and this is the SPEF. So if you see, I have taken from result routing USB.spef, which I was showing few minutes earlier. So this is the step rating and this is the clock, and again 12.55. If just let me quickly show you how to do this. Launch STA, source run.pickle. Your design loaded. This is showing some warnings that is saying your antenna cells has not been found in .libs. So there is an open question for you: why antenna decap cells are not included in .libs? We'll perform a report checks. Yeah, this is your time report. So what I said, even if your slack is met, you will not find it in the reports because that is not a violating path. So if you want to interested in doing the timing analysis, then even though your timings are clean, then also you can do it simple. This is the, you can do like this way. You can do any design STA at any stage. Yeah. Next we have, I have captured a few images from Magic after loading the def in the Magic tool. So this is how my floor plan stage chip view results. So here, as we discussed, we will have a floor plan and we will have a PDN network created. So these strips are of power domain. So there will be VDD, VSS, somehow nomenclature is not there, but yeah, we can figure out this is my floor plan and these are my power networks. Then next is at how it look like a placement stage once your standard cells, macros, IPs has been placed. So this is how you will find your layout to be with your standard cells is placed. These are placed according to the coordinates and the tool placer has been placed, constraining the things like timing aware placement or that is power aware placement. That's the strategy that tools adopts and does the placements. Next is standard cells view. I have zoomed in that view, and this is how you can find the name. So this basically, this top one is your standard cell name that you will find it .lib left everywhere, and this underscore 1490 is your instance name. So there is a possibility same standard cell could have been placed multiple times. Below that, if you see, this name is same till 4, and the below number 90, there's a 94. So these both cells are same, but this is a copy of it. That this cell has been used twice, and this, if you see 88, this is thrice. So these are these different instances that has been placed. Now, how my layout looks like at the routing stage. So this is again the layout with the standard cell placed with filler cells in it, antenna cells, decap cells, all those filler cells insertions and all those things. Above that, routing has been done. So this is complete base layout and your layers layout. Complete GDS looks like this. Future scope, that's important. Whatever we have discussed now, what we can do now. One thing we have studied is we can practice it. Other than that, what can be done? First thing is learning becomes easier and more practical. So you might be taking a skill set on STA, PD, DFT, verification, RTL writing. These tools help you to work on your own pace at your home, and you can easily understand and relate the concepts which you are studying in theories. Next thing, you can get layout of our own RTL design. Let's say if you are interested, you are in final year, or even though you are not in final year, you want to do a project that says I have designed layout of an RTL. Go to open source. There's a site opencore.org that provides you RTL of different things. You can download them and do complete synthesis, art synthesis, physical design, and then layout. You can do that. Third thing, contributing in enhancing the capability of these tools. Again, coming back, these are not these industry standard tools, but open source community is trying to imitate the features of those tools. So again, one of the best feature I can mention here, which is not in OpenSTA. So if you see Primetime or Tempest, they can do your crosstalk aware timing analysis. They can do that, but this OpenSTA cannot do. So what you people can try is, if you're good at scripting, good at coding, logic building, you can write, you can edit these codes since these are openly available. You can even contact the contributors who have generated these things. You just go to GitHub, you will find email address and all the things. Start contributing it. One of the advantage of, if you do these things, then you are opening your chance to get into a EDA tool industry, that is Synopsys Cadence, because all the thing that Synopsys Cadence mentor graphics are working is they are building these EDA tools. So if you are helping or contributing in these open source tools, then definitely you can work there. So you are making, you're just stepping ahead to get your placement. Yes, that was all I was having. And we have much more things with us. Stay tuned. We will be sharing few more webinars and these tutorials, workshops. Let's
That's
see if
great.
we have
I think
questions.
no, I think no need to ask people like whether they have any question or not, because they had a lot of questions, and your team did the fantastic job, I would say. So they just answered each and every question. So they saved your time and they saved everyone's time, I would say.
Yeah, thanks a lot, Manisha, Yanesh, and Hemant. They even yesterday night when I was stuck somewhere, Hemant was helping me at 1 a.m. So
That's
very thankful. Yeah,
the power of a team.
right.
Great. So great, guys. So I think it's just a start, and I can see few of you have just mentioned like, okay, it's good. Like Rajat explained you such a nice way the different PDK and the different open source tool, and I really appreciate. I know, like, okay, interest of a time, he skipped couple of things which he had discussed with me. Like, okay, he will show you like all these magic related things. So initially the plan was like he will just pull up all those layout and he will just show you. But it looks like you guys are uh, almost like more than 2 hours. So so he decided, he just messaged me like, okay, we will do that particular part later on. I think that's a good thing. But yes, don't worry, don't think like, okay, he just draw those layouts using any paintbrush or something. Everything is captured by the magic only, so you can yourself run it and see and verify. And if you will see like, okay, he copied any particular picture and just do it around there, maybe just and then you can just post, and then you can just come back and you can just tag him over the LinkedIn, and you can say like, okay, see, this was not my result, this is something you you did it in a webinar. You can do all those things. Get thanks a lot, Rajat. So Saroj sir is there, so yeah.
Yeah.
Sorry, sir. I was like, was just talking.
No. That's good. No, thanks a lot. Great presentation. I feel bad I took 15 minutes of your time. So,
That's not completely fine.
And thanks a lot to who's there, Hemant,
Hemant, Ganesh, Manisha, and Rajat.
and who's third person, I forgot. So yeah, they did a great job of answering the question. Like Puneet, you said, basically they saved 45 minutes of Q&A. It was happening parallelly as you were doing it.
So, sir, I was thinking after this these three people were playing this Q&A sessions, like next time onward we will have a separate team who can answer in all the workshops and the presentation. That will save a lot of
Yeah,
time.
actually, especially with workshop, I think this is a great. I mean, with talk you can't do that because the speaker is speaking,
Yeah.
unless the speaker puts a team, right? But for workshop, I think this is a great idea because you can just put a team and saying just keep answering it, and the ones which are not will take it in the end. So yeah, it's very efficient because while people are doing, because there's a lot of time where you're trying things and out, so people can just ask question and get it. So I think yeah, for workshops and tutorial, I think it works great.
Yeah.
So I like the idea because now we would have spent another, which is okay, but this is more efficient to do that. So yeah, a lot of people, like as you said, they're just very thankful, and 100, at least on Zoom, there are like 130 people still sticking around. I think another 100 plus on YouTube. So that for 2.5 hours, almost 2.5 hours. So so that's, we don't have to say that it was great. I mean, Rajat, I think that itself proves that it was a great session. So yeah, thanks a lot. And I think a lot of people now know about the open source flow. I did want to point out one thing I've seen. I mean, nobody asked that question here, but a lot of people ask this question, what's the difference between the GPDK and the open source SkyWater PDK? Because, like Puneet mentioned that what can you use it for? Interviews, because you can actually try things out. So that's what people use, actually, the GPDK. But the GPDK is like a synthesized PDK. It's not like you can't fabricate in it. So there might be some things in that which are not real. I mean, they're made out of it. So that's why they're never like good for the full flow. But with this PDK, it's actually a real PDK where you can actually go and fabricate. It's still in beta stage, but you can do. So that's one thing I wanted to just point out. Okay, anything else, Puneet? Or okay, before we stop, don't forget, tomorrow 10 o'clock is, so tomorrow is the carrier day. So guys who are, I think most of you are, VLSI aspirants. So I would say tomorrow is the day for you, because we have two great talks. First one is Narsaya from Savia, and he's, he's a great designer, but he just explains things beautifully too. But he'll be it won't be a technical, he will be concentrating on skill sets, but don't miss that. He will give a great talk. And then obviously Puneet is, he's the de facto standard in the industry now for carrier counseling. So you obviously don't want to miss that. So that'll be at 11:30 by Puneet, and Narsaya at 10 o'clock. And then we'll just have a short closing statement. That'll be it. So don't miss tomorrow. I think it's been great participation, and the talks and tutorials and workshops so far, I feel has been great. So I think it'll be a good day tomorrow too. So thanks a lot again for everyone having the patience to stay tuned for the whole day, and look forward for the tomorrow's talks. Okay, any closing stuff for Puneet? Or
no, so closing is same. Thanks a lot.
Okay. All right. Thanks.
Closing from my side. Thanks a lot for providing the opportunity to present it here and represent my company also.
Yeah, it's our pleasure. Thanks again.
Yeah.
Sure, we'll work with you, in future on some things. So
sure.
Yeah.
Even there are many more webinars planned with Puneet sir on these tutorials itself. So we'll be coming up with that.
Sure. And now, people know what it is they got introduced. So I'm sure there'll be a lot of interest to that as well. Okay. All right. Thanks again. Bye, guys. Good night.
Bye-bye.
Okay,
Bye, Rajat.
thank you.
Bye, Sir. Bye-bye. Bye, Hemant. Ganesh. Bye-bye.